Play in the home game. Those of you play in the home game. The question was, when I ask for an answer for this, like this question, like for example, the question is, what percentage of all Bend for sale homes were in foreclosure? You feel completely comfortable telling me that the confidence interval, the number at the top of the TI, or the numbers, I should say, the range of values, oops, at the top of the TI, I'll run another one here really quickly. This is a perfect answer. I want you to know what it means, which is why I verbally say it. We are 95% confident that the percentage of Bend homes is at least 9%, but at most 9.5%. You can write that whole thing out if you want to, but as long as you understand the numbers you're looking at, that's what I'm after. And the question itself, give the 95%. What you'll often see is give the 95% CI for the percentage of Bend homes in foreclosure, or the percentage of Oregon homes in foreclosure. And when you give me that, you've done that. You've given me that range of possible values. Go ahead, Susie.
If you want that instead of like PCAT equals 9.2%.
Plus or minus. You can totally, Susie asked, could we also go 9.2% plus or minus 0.25%? It's the same thing. Apples, it's potato for me. So I think it's easier personally to give me this, but for you guys realistically consuming journals and consuming news, it's probably going to be more useful to be able to do that. The p-hat's going to be up here, the margin of error is down here, put them together. But on an exam, don't make more work for yourself than you have to. Just go ahead and give me the values here. Is that fair?
Yep.
Cool, cool. So what I want to do next is I want to present you with some other data that I want you to estimate. So I used to play in a thrash band called Hands on Throat here in town, and we used to practice on Wednesday nights. This was pre-max, and yes. All right, here we go. And I used to stop, this is back in 06, 07, 08, and I used to ride my bike from work down to practice. We practiced like 4 hours playing like, 212 BPM, punk rock music. You get hungry. So I'd stop at Del Taco and pick up some burritos on the way down, which I know is not the best thing to eat, but I was burning about 5,000 calories in 4 hours, so I didn't feel too bad about it. And I started noticing that they were calling them Del Taco half-pound bean and cheese burritos. I said, what does that mean? So of course, what I said,
just can't eat the burrito. Just eat the burrito.
Well, I did for a while. And then you fall into it's just like anything else. You fall into a habit. Some things become automated and your brain starts wandering and thinking other things. So I started looking at the package. Half-pound bean and cheese burrito. What does that mean? So I talked to Bruce Emerson over in the science building. I was like, Bruce, do you have like a wickedly precise scale? He's like, yeah, what do you need it for? I'm like, I gotta put it in my backpack once a week, take it to band practice, set it up on top of Ray's Marshall half stack, and weigh some burritos. And he's like, Sean, here you go. I don't know what the hell you're talking about, but go ahead. So I borrowed his scale from the science building, and I grabbed 30, not all at once. I tried to make this as pseudo-random as I could. So what I would do was, I would actually generate a random number from 1 to 4. I used to eat 4 before practice. So I buy 4, and I generate a 1 to 4, and I'd weigh that many each time. So I wasn't always weighing all 4. Sometimes I was weighing 1, sometimes 2, sometimes all 4. And I tried to change the day of practice every once in a while to get a different day, because people that are on a weekly schedule, the same person's in the restaurant every week. If they have the same kind of habit, I'll be measuring their bias. So I tried to mix it up a little bit. Granted, it was the same restaurant every single time, so we got some bias in there. But here are the weights. Here are the weights that I came up with for the 30 burritos that I measured.
You're like those guys that sued for 11-inch...
I was not going to sue anybody anything. I wasn't going to sue anybody for anything. I was just curious. If you take this too far, you could, theoretically, maybe. So I guess my question is, why is a Del Taco half-pound bean and cheese burrito called a Del Taco half-pound bean and cheese burrito?
Because on average, you're going to get a half-pound of food.
Are we?
Let's find out.
That's the question, right? The question is, I love that answer. That was my first thought. Because as I look at my data, it doesn't guarantee me half a pound of bean and cheese every single time, because there were some times I didn't get it.
Right.
Right?
Minimally.
But there were some...
On average, you got more.
See, this is the whole thing. On average, what does a half-pound bean and cheese burrito from Del Taco weigh? Now, can the tools we just learned answer this question for us? Carrie's saying no. Michael's seconding no. Michael, what do you really think? I saw motion, I'm sorry. I'm like an amphibian, I see motion. Oh, you're fixing your hair, sorry, my problem. I heard Carrie, why did you said no almost immediately? You said no, that tool we have does it.
Because you just need to put it into L1 average.
So, we're talking about a different parameter, aren't we? The previous parameter was a percentage. Could we test percentage above half a pound?
Sure.
Yeah.
We could do that. We could test the percentage of burritos above. Let's do that for practice. Why not? Let's do that for practice. Let's, based on this sample, where can I put this so you can see the data? I'll just put it up there for the time being. So here's 30. We got a sample size of 30, which is very, very small. We have to set a pretty wide margin of error for this one. Maybe. Depends on p hat, I guess. Of the 30, how many came in under, or how many are over half a pound? So, 1, 2, these are all under. 2, 3, 4, 5, 6. So 7. So 7 came in under. 23 out of 30 were half a pound or more. Let's run the interval for 23 out of 30 as a representative sample of Del Taco half pound bean and cheese burritos. And let's see, yeah, that's kind of faint. Let me read this screen. So let's. So 23 out of 30 at 95% confidence. Let's calculate that. So I end up, now check out the margin of error, friends. It's got to be huge, doesn't it? Your sample size is 30. 30, right? Now minimally, that whole Christian n times p bigger than 5 thing has to kick in. So if you have 30 burritos, 30 times whatever the percentage is has to be at least 5. That's probably enough as a bare minimum. But you can't guarantee things like 3% margins of error with 30 burritos. But what this tells us is, based on this interval, no matter how wide it is, does it look like at least half of the Del Taco half pound bean and cheese burritos are coming in over half a pound?
Yes.
It does, because what's the least possible percentage value?
61.
Right, about 61.5%, which is above 50%. So even with a ridiculously wide, 15% margin of error? Even with that wide margin of error, if this data is representative, then it looks like at least half of the burritos are coming in over half a pound. But that isn't the question I asked, is it?
No.
The question I asked was, how much do they weigh? How much do they weigh? And that's why we have to actually use the weights themselves. I needed to use the scale to get their relative weight, but I wanted to get down to that. I asked Bruce for his scale to get that kind of precision. Thousandths of a pound precision, which is ludicrous. It's like a piece of cheese, thousandth of a pound. So Carrie is already on it. I can see her back there. She told me what to do. In order to know what the average weight of these Del Taco half pound bean and cheese burritos is, we have to analyze. You guys begin crunching. Begins crunching, and I'll do it up here too. I'm going to mute this. Actually, no, not mute the screen because you need to see it. So I'm going to leave the screen on. Throw in L1. Stop talking. Oops. Folks at home on YouTube, I apologize for the delay. We'll resume our regularly scheduled program soon. Ish. Ish. I've heard that word's catching on around campus. I'm pretty excited about that.
It is.
I hear administrators using it now in meetings. That makes me very, very happy.
Rutgers is using it in the social class.
No! That's awesome.
We were talking about you the other day too.
Yay!
Wait,
Oh,
you don't know what
Rule.
they said.
Of course, Rule. Rule has this to say about it. SOB. So, as you're entering data, let's take a look at where we were and where we're headed. There's definitely some overlap here. There definitely is some overlap. Let's slide the sideboard here. Oops. Hello, microphone. Battery is batterying. Estimating little p using little p hat. This is what we were just doing, and we just did it literally 3 minutes ago. by checking the proportion of burritos that came in over half a pound. So, as a recap of where we just were, when you estimate little p using little p hat, you start by taking your random sample, simple random sample. You generate a p hat, which is the center of your sample. Then you generate a margin of error around that. Or in this case, let technology do it for us. We learned that from yesterday. And then you create that margin of error with the 95% confidence assertion that once you add and subtract, I was using MOE. Once you add and subtract that margin of error from that p hat center, 95% of the time, the fishy that Christian is calling p is going to be in that interval. Perfect, perfect. So the parameter you're looking for is going to be within your margin of error of p hat 95% of the time. That's the big idea. That's the big idea of the first part of this course. However, the problem is this only works when you're trying to estimate a proportion. Here, we're not trying to estimate a proportion. We're trying to estimate what?
An average.
An average. We're trying to estimate a mean or an average. And we talked about 3 measures early on in this class, and you've probably already forgotten. It's totally okay if you have. There are 3 unbiased estimators in statistics. Little p, mu, and the population variance. We're going to deal with that today in a sidebar of dealing with mu. But really, this is one of the 2 confidence intervals. We're going to have that lead us into estimating mu using who? Who are we going to use, do you think, to estimate mu and build a margin of error around it? Which one? X bar. Yes, the average for sure, Carrie, but the sample average. Think about what p hat is to p. P hat is the sample proportion to the population proportion of little p. X bar is the sample average to the population average mu. There's your correlation. And it's all going to start the same way. You're going to start with a simple random sample. Pretty much everything starts with that. Or at least, if you don't have a simple random sample, you have a pseudo simple random sample. Pseudo simple random sample. Because you can't always get a perfectly simple random sample. In order for this to be a perfect, simple, random sample of size 30 of Del Taco half-pound bean and cheese burritos, where would I have to go? I'd have to potentially go all over where there are Del Tacos. Because the basic idea of a simple random sample of size 30 is that any particular sample of size 30 has the same chance of being chosen. As it is, the Del Taco in my hometown of Wilmington, Delaware has no chance of being chosen because I didn't bike by there on the way to hands-on throat practice, 6,000-mile round trip out of my way. So, I've got a pseudo simple random sample. The pseudo part is because I went to the same one every time. The simple random sample is, even though I was going to the same one every time, I tried to mix it up as much as I could. This happens in research all the time. All the time. Your first project deals exclusively with this. First, it deals with that quite a bit. From that simple random sample, we are going to find the center, which we're going to call X bar. Have you guys found him already? Have you guys found him already? I'm going to mute this screen now. He's over here. Let's mute this bad boy. Come on over here. There we go. Fire you up. So we got L1. Let's go to stat calc. Just an L1, right? So we just hit enter. All right, friends. So I now have. I can erase the real estate data. I now have a bunch of stuff to peruse. I've got a sample average. This is Del Taco half-pound bean and cheese burritos. Yes. Yes. So I've got an average weight in my sample of 0.526 pounds. Fantastic. So I can go back to my constituency and say, yep, you're getting on average half a pound because my sample came back at just over half a pound. To which you say, no, because why?
Because we have to plug that in via the margin of error.
We have to have a margin of error around that. The only way I could report that number right there is if I did what? If I had sampled every possible Del Taco half-pound bean and cheese burrito in existence and averaged their weight exactly, Lindsay. That sounds disgusting. And it sounds impossible because I'm sitting here talking to you, they're making more of them. And some of the ones I just measured got eaten. So the problem is you can't do it, so you have to draw a sample, and that's okay. But because you have to draw a sample, you have to attach a margin of error to it. So essentially, the next step at this point, is to create x bar minus said margin of error and x bar plus said margin of error, so that 95% of the time, the average you're looking for falls between those two values. Does this make anybody's stomach turn at all, seeing this? No, because why? Just a little bit, just a little bit. Christian, go ahead.
Do you have to do, because you have 5 number summary there, right?
Down, lower, will, yes sir.
Right, so you have that average, do you also need to plug it into what we did first so that you get the margin of error?
When you say what we did first, what do you mean?
On the sheet with the fish, like the C.
Good, thank you. Hold that thought 30 seconds, Christian. Great question, great, hold on to it. So this doesn't make anybody nauseous, because it ties back to this. It's the same thing as this. I like asking that question at this point in the term, because I dropped something like this on you guys at the end of 243, and I could hear dry heaves. I could. When we did the central limit theorem, I had almost the exact same thing on the board. I had the x bar minus, I wasn't calling it margin of error, I was calling it 2 times standard error. Which is essentially the same thing. 2 standard errors becomes 1 margin of error at 95% confidence. And just, I knew, it always happens every term. Like that slide pops up and people go, oh. Because everybody's happy, we're rolling dice, we're taking quizzes, we're happy, we're getting it. And then I show you that, they're like, nah. But this is all it's saying. It's giving you the extreme values of Ashley's distribution. It's all about that distribution again. Except Ashley's distribution back here was centered on the population proportion little p. This distribution over here, go ahead, say it again. This is going to be centered on mu. And your x bar is going to fall somewhere around mu, but not on it necessarily, most likely, which is where the margin of error comes in to make sure that 95% of the time you pick it up. So the question then becomes is, how do we form this margin of error? So, I want you to look up there. Christian, what you said, 5 number summary, I love that. Look at all these numbers, all these beautiful numbers up here. His first question was, should we do it like we did with the 1 prop z int? The answer to that is we can't. We can't, can we? Because in 1 prop z int, we were measuring a percentage. And the entire margin of error, p hat q hat over n square root, is a percentage. We need a margin of error, a measure of variability based on the actual weights. And I think, Michael, what are you saying?
Well, at that point, we should just multiply the percentage by by u and on both ends, and then you would get
What percentage?
the percentage that you got off the z int.
The problem is, the z int is answering the wrong question. The z int is answering the question, what percentage of burritos come in over half a pound? I don't want to answer that question. I want to answer the question, how much does a half-pound bean and cheese burrito actually weigh? So I need a measure of variation that talks about the pound. Karen, what do you see up there? What do you see up there, friend? Please do, because I think you're pointing the right thing.
Zero variation, right?
Him. Isn't he a great measure of deviation within a sample? He's fantastic. We have to edit him because he's not inferential yet. He's just descriptive right now. So we're going to use the central limit theorem stuff we talked about in 243 to edit him down. We don't need him, we don't need this. This is great stuff. It's not necessary for this. We can't use that, can we? Why? Because that assumes that you have the entire population in your TI, which is silly. We are going to use this. This is important. But keep that in the back of your mind. And the 5 number summary that's down here is all fantastic, except for the fact that this stuff is relative position versus the absolute position that's measured by x bar and little s. So we definitely, friends, we definitely want to use the standard deviation of those weights. We definitely want to use the standard deviation of those weights being about 0.025 pounds. We definitely want that. We definitely want to use that. The question, I guess, is how do we use that? So, go ahead, Michael, go ahead.
If we're looking for 95% of the population, wouldn't we multiply s weights times 2? And then,
I'm just drinking this in. I'm getting real happy right now.
Well,
I'm not going to lie to you.
Then multiply that percentage plus or minus the mu at that point.
Here Michael just said, I love it. He said, okay, there's your standard deviation. There's your standard deviation. We're going to multiply that times 2. And then add and subtract that number from 0.526. Let's do that real quick. So this is, times 2 is about 0.05. Now that's not 5%, that's 0.05 pounds. Remember, these are not percentages, these are weights. So this is 0.05 pounds. If I add and subtract 0.05 pounds from 0.526, let me see if I do this in my head, 0.476 up to 0.576, did I do that right? Did I do that? If I do x bar plus or minus 2 s's, I should get 0.476 pounds up to 0.576 pounds?
Correct.
Is that correct? Okay. Let's pause and stop right here for a minute. When I look at that, if I want to use that as my confidence interval, can I now make the claim that on average, a half-pound bean and cheese burrito from Del Taco weighs half a pound? Can I now make the claim that a Del Taco half-pound bean and cheese burrito, on average, weighs at least half a pound?
Yes.
Can I make that claim based on that interval?
Yes.
Yes.
Where's the fish?
Anywhere.
Where's the fish? Anywhere in that interval, right? So let's draw a picture. Let's draw a picture. We haven't answered the question yet, friends.
The fish falls below half a pound.
Could fall below half a pound, can't it? Right?
Fish
That's
has
the
a-
uncertainty principle.
Greater chance of being.
Hang tight, Jared. Hold that thought. I love that thought, by the way. Hold that thought, though, okay? So here's half a pound. That interval starts down here and stretches up here. Now, Jared's point is that there's more of the interval on this side than this side. There's a decent amount of credit to be given to that idea that it's further on this side than this side. But we can no longer guarantee that on average a half-pound bean and cheese burrito weighs half a pound because of this chance down here. You see what I'm getting at here, friends?
Because you
still
only
have
have a small
basic-
sample.
Exactly. We still have a small sample. Believe it or not, it's actually a small sample with this kind of data is legit. More legit, I should say, than a small sample with proportional data. More of that to come. More of that to come. Hold that thought, Susie. Now, Michael, we do have one correction to make, though. When we do x bar plus or minus 2s, and we create 0.476 to 0.576, we haven't actually answered the question. In general, are Del Taco half-pound bean and cheese burritos half a pound? Can anybody see why we haven't answered that question? This is a very, very hard question to answer, and it might not be obvious to you, and it's okay if it's not.
Because 76% of the time they are.
When? Where? Who? 76% of which ones? The
Oh,
ones in my sample.
yes.
This is a descriptive interval, friends, not an inferential one. In other words, we're not allowed to make that interval stand for the entire population because it only stands for a sample. We have to adjust to make that. This is not a standard error yet, friends. This is not a standard error. It's a standard deviation. And this is tricky, and this is not at all trivial. A standard deviation, Sx, is the measure of variation within your sample. Just like in 243 with the funny dice I made you guys roll, you guys all got a standard deviation of your samples. But you noticed that standard deviation changed once you started rolling them more than one time. The same thing has to happen now. What happens as your sample size goes up? What happens to your variation? It goes down. Do you remember as a function of what? Do you remember as a function of what? You divide by, you might not remember this, it's okay if you don't, it sounds like you don't. The square root of,
Is it p?
you got it, Dustin, the square root of n. Do you remember that? You can say, no, it's been like 4 weeks. Of course you don't. So here's the deal, Michael, I love this idea. I want to come back to it if it's okay with you. I want to come back to it if it's okay with you. But we can't use that interval because that only speaks to our sample. What we have to do is, we have to take the standard deviation of the weights, which is purely descriptive with respect to the sample. And we have to correct it to make it inferential. There's no correction needed on the average because the average already does a good job inferentially. We proved that back in 243. We proved it again about last week here in 244. It already does a perfect job. So we have to correct it to get the standard error of the weights, which makes it inferential. And the way you do that is you take your sample standard deviation and you divide it by the square root of n, which is what the central limit theorem gave us back in 243. I know it's been like a few weeks back. We've probably forgotten it. That's okay. It's okay. You bought it then, and you'll buy it again as we get into here. And you can see why this is good. As your sample size gets larger and larger and larger, this starts shrinking away until eventually, essentially, it's 0, which means x bar and mu are the same thing. which would happen, wouldn't it, if you sampled enough of the population? Your average would hone in on the center of the bell curve. So for our example, it's going to be 0.025 divided by the square root of 30. Let's get some accuracy on that and precision. So we got 0.025 divided by the square root of 30, which comes up being 0.005 pounds. These are all pounds, right? Pounds. 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 Why do you use LBS for pounds?
I don't know.
Is that a British thing, yeah? It's got to be. When bastards. So, much, much smaller. Much, much smaller than the sample standard deviation. That's because this is the central limit theorem kicking in and making our estimate inferential. Now here's the problem. I call that a standard error. Is it a margin of error yet? Either answer yes or no would do for this. I like your answer, Carrie. No, because how much confidence would I have right now if I use just that number? Say it. Say it, Darla. 68%. That's one standard error, which goes